Hello, I'm Yongdong Kim from Dongguk University DTM Lab. Today I'm going to review a paper titled Identifying Technologic Opportunity Using Dual Attention Model and Technology Market Concordance Metrics. This slide shows the bibliographic information of the paper. The paper proposes a framework that integrates dual attention web mining with a text embedding based technology market concordance metrics. The authors aim to build a more accurate and scalable approach for identifying technology and market opportunities using both corporate websites and patent portfolios. By combining keyword extraction, machine learning classification, and concordance mapping, the study provides a fine-grained technique for understanding firms' strategic directions and potential innovation areas. Here are the contents of today's review. This is the introduction of the paper. The authors highlight that firms increasingly rely on technology opportunity discovery to expand their innovation boundaries and react to emerging market trends. Traditional concordance metrics relies on coarse industrial classification which fail to capture keyword-level market signals. At the same time, corporate websites contain rich market information, but the raw data are noisy and unstructured, making it difficult to extract meaningful technical keywords. Therefore, the purpose of the study is threefold. Develop a dual attention model to automatically extract technical keywords from corporate websites. Second, constructs a technology market concordance matrix using text embeddings from patents and web keywords. And third, discover technology and market opportunities at both industry and farm levels through the indicators of technology proximity and market proximity. The literature review begins with prior work on technology opportunity discovery. Earlier studies defined TOD as the process of identifying new possibilities to advance technological fields. Much of this work distinguishes between incremental innovation, extending existing technologies, and radical innovation, which focuses on emerging or disruptive technological domains. Patent text mining and roadmap analysis have been widely used for this purpose, since patents contain structured and detailed technical descriptions. However, while patents are comprehensive, they tend to lag behind real-time market movements, which creates limitations when detecting early signals of technological change. Because of this delay, recent research has increasingly incorporated alternative data sources such as trademarks and corporate web content to supplement patent-based analysis. The review then moves to the role of web mining. Web data provide large-scale, publicly accessible, and relatively unbiased information about firms, activities, and market positioning. Prior studies categorize web mining into contents, structure, and uses mining, and many recent works have used web content specifically to examine how firms communicate technological capabilities or commercialization activities. Through keyword-based analysis, web data have been shown to offer valuable insights into firms' market perceptions, competitive strategies, and emerging technology domains, which makes them a strong complement to traditional patent information. Advances in attention mechanisms in NLP offer tools for extracting salient information from large, noisy text sources. Attention improves focus at multiple levels: word, sentence, and document, forming the basis for dual attention models. Research on technology industry concordance metrics highlights the value of linking patent technologies with industrial fields, but past approaches rely on coarse classification costs, limiting granularity. These have motivated newer studies to adopt text embedding based methods for finer technology market linkage analysis. In this study, the authors combined corporate web portfolios with patent portfolios to analyze technological and market opportunities simultaneously. For the web data, financial records from 4,530 listed firms are used, and 3,829 company websites are collected through a corporate identifier. Only pages within the same domain are included, excluding SNS links to maintain consistency. For the patent data, information is taken from METI and matched with JPO text such as titles and abstracts. Based on these records, the authors identified 1,798 high-tech firms and 2,040 non-high-tech firms, forming the foundation for later modeling and comparison. In this study, the authors introduced a dual attention model designed to identify technical content hidden inside corporate websites. The key idea is that high-tech and non-high-tech firms are use noticeably different technological terminology. The model learns these differences and uses them to filter out web pages that contain meaningful technological information. The architecture consists of two hierarchical attention layers. First, the word level attention assigns weight to individual tokens through a softmax mechanism. This allows the model to focus on terms that are strongly associated with technological capability and to downweight generic or irrelevant wordings. Second, the page level attention applies a sparse-max distribution to highlight the few web pages that carry concentrated technical signals. Because sparse-max can assign zero weights, it effectively removes noisy pages such as marketing or corporate identified content. For consistent training, all web pages are padded or truncated to fixed lengths. This pre-processing ensures that web page vectors can be aggregated into firm-level representations in a stable and comparable way. On the right side of the slide, the figure illustrates how the two attention layers interact. The word level layer extracts salient tokens within each page vector, and the page level layer then determines which pages contribute most to the firm's final representation used for classification. The next part of the methodology describes how keywords are extracted from web data. The model uses attention weights generated at both the page level and the word level. Page level attention, implemented through SparseMax, determines which web pages are most relevant by assigning non-zero weights only to informative pages. Word level attention, based on Softmax, then highlights the specific technical terms appearing within those selected pages. To control the amount of information extracted, the authors apply a percentile threshold so that higher thresholds produce a concise set of highly relevant keywords, while lower thresholds keep a broader and more diverse set of terms. After extracting keywords, the study evaluates their effectiveness. Both the raw web data and the attention filters keyword sets are transformed into document vectors using LDA topic modeling, where topic distributions function as firm-level feature representations. These vectors are then used in classification tests designed to distinguish high-tech firms from non-high-tech firms. Several machine learning algorithms, including logistic regression, SVM, and random forest, are applied for comparison. Across these experiments, the keyword-based representations consistently outperformed the raw web content, demonstrating that the attention mechanism effectively filters out noise and preserves the technical information that signals a firm technological orientation. The results first describe how the web content was prepared and how the dual attention model was trained. Core web pages were initially filtered through a language identification model to ensure that only Japanese language pages were used, allowing the dataset to remain linguistically consistent. After this, the text was cleaned using MeCap, which removes punctuation, stopwords, and other noise. To standardize inputs for the neural network, each firm's web portfolio was converted into a uniform set of pages with fixed token lengths, using padding and cutting so that the model could process all samples in the sample format. Using this standardized input, the dual attention model was trained to distinguish high-tech firms from non-high-tech firms based on terminology differences observed in their websites. The model then generated attention weights, which were used to extract keywords representing each firm's technical and market-related information. Because the quality of extraction strongly depends on how much meaningful content a firm publishes online, the method performs best when firms have sufficient web coverage and may require resampling when datasets are imbalanced. The second part of the research evaluates the quality of the extracted web information to test whether the attention filtered keywords truly enhance firm-level characterization. The study compared classification models trained on raw web data with those trained on extracted keywords. Both forms of text were transformed into topic-based vectors using LDA so that the same feature representation could be applied. Server machine learning algorithms were then used to assess discriminate power. Across all models, the representations built from extracted keywords consistently outperforms those based on raw web content, showing clear separation between high-tech and non-high-tech firms. Random forest is in particular showed the strongest improvement, indicating that the extracted keywords capture the essential technical signals that would otherwise be diluted by noise in the original web pages. This section explains how industry-level opportunities are discovered by linking firms' technology profiles with their market signals. Two concordance metrics are constructed to model this relationship. Matrix A maps how technologies translate into market domains, while Matrix B captures how market needs point back to relevant technologies. Technology vectors are derived from patent-based embeddings, and market vectors are aggregated from the extracted keywords and web page information. Using a set of high-growth firms, the study estimates both metrics so that early innovation trends and translation patterns can be detected. Opportunities are then identified by comparing predicted vectors generated through the concordance metrics with the actual technology and market vectors observed in the industry. Where large gaps appear, the framework interprets them as potential opportunities, either indicating unmet market needs or underexplored technical directions. As an illustrative example, the automobile industry reveals distinct patterns. In the terms of market opportunities, areas such as computer technology and control systems appear more promising. On the technology side, semiconductors, environmental technologies, and surface coating materials emerge as important innovation directions that automotive firms may increasingly rely on in the future. This section explains how the study identifies opportunities at the individual firm level. First, two indicators are computed for each company. Technology proximity measures how close a firm's patent-based technology vectors into various IPC subclasses. Market proximity does the same on the market side, comparing the firm's web page-derived market vector with market-relevant IPC subclasses. Higher TP or MP values indicate stronger alignment with specific technological or market domains. Using these indicators, the framework constructs a two-dimensional opportunity map. The map is divided into four strategic quadrants, allowing firms to be positioned according to their technological strengths and market alignment. Quadrant 2 represents areas suited for technology-driven market entry, while Quadrant 4 highlights market needs that can guide future technology development efforts. As an example, Company H is mapped across both quadrants. It shows technology entry opportunities in areas such as C23G, C04B, and B01J, while market-driven technology opportunities appear in H01M, H05K, and H02S. These findings align well with the firm's existing activities in batteries and semiconductors, indicating clear potential for targeted R&D expansion. This study contributes an attention-based method that extracts cleaner technical signals from corporate websites and a technology market mapping framework that combines these signals with patent data. Using this framework, the authors identify opportunities at both industry and firm levels through TP and MP indicators. For limitations, the analysis relies only on current web pages, so future work includes using historical archives like the Wayback Machine. The method also depends on patent-based variables, which may overlook startups. Applying the model to specific industries and testing alternative baselines are suggested directions for improvement. Thank you for listening my paper review.